Okay, so indeed, we just got email from Fernando 5 minutes ago that he had been totally brutalized by his flight and was barely able to move. Which is fine. I put something together last night, and the idea, so the title of this is intro to quantum entanglement. And I'm going to get pretty elementary in this lecture. I'm going to talk about some things you've seen in Patel's and maybe even in Matt's lecture, and just work through, reintroduce density matrices and where they come from, and say a few things about open quantum systems. And then I'll go back and work through a couple examples of applications of quantum entanglement that sort of sit at the base of quantum information theory, just to give some intuition for the subject. If I have time at the end, I'll talk a little bit about quantum thermalization, but not in any serious way. Okay. So the quantum entanglement is probably the central feature, at least to my mind, that distinguishes quantum information theory from classical information theory. And the basic point is that if I have two components, say, a system in quantum mechanics is, of course, described by a Hilbert space. I'm going to imagine I have two components of this Hilbert space. So this is a tensor product of two separate Hilbert spaces, and in a general state, I can write times where I is a basis for when we're talking about entanglement, we're talking about situations like this where I can break up the Hilbert space into factors. And the basic point of quantum entanglement is first that measurements of A, depending on what the measurement is, correlate with certain measurements. So the first thing that happens in a quantum entanglement situation, we'll work out the canonical example in a second, is that any measurement, it corresponds to a situation first where any measurement of this will tell you something about what a measurement of this will give you. But the second thing is that the overall outcome of either measurement is not typically determined. So entanglement is the combination of these two properties. Overall, you don't know what you'll get when you make a measurement, but you can be assured, in a situation with entanglement, you can be assured that a measurement of one system will tell you what the other measurement of the other system will do. So the underlying point is that in this superposition, quantum superposition is central. It's important that I can have, for example, situations where a state could be a linear combination, say a spin could be a linear combination of spin up and spin down with respect to some axis, or superposition includes things like the double slit experiment, where a particle is sort of a linear combination of having gone through two slits, which you can record by looking at interference patterns. Okay, so the classic example is the state of, which I think both Matt and Apurva have discussed. It's just the case of two spin half systems So here, by which I mean HA, is the Hilbert space is just two-dimensional, like so, and a basis for HA or B will just be all labeled like this, such that so I'm mostly going to be talking in this hour about these kinds of spin one half systems, and if I choose the essential point is if I choose an axis, say the z-axis, I can measure the spin along that axis, and there are the two possible answers correspond to orthogonal states and provide a basis. So these are sometimes these are called qubits. We'll talk about these more. A single spin one half particle would be called a qubit because if I make a measurement of SZ, I get two answers. Of course, as I'll discuss in a bit, a qubit can take far more states than just those two. I can get any linear superposition of spin up and spin down. And so the following state in the full Hilbert space I can choose, there are a number of states like this, but I can choose this state, which among other things is the state in this Hilbert space with total spin 0. And here, if I make a measurement of the spin along the z direction of A, it's guaranteed to be anti-correlated with the measurement of the spin along B. On the other hand, if I don't know what's going on with B and I just measure A, what is the outcome of that experiment going to be? Anyone? Anyone? Speak up. If I just make a measurement of the spin, the z spin along in the first qubit in A, how do I describe the outcome of that experiment? What will I see and with what probability? Yes. So if I just make a measurement of say, the first spin, I will measure either spin up or spin down with equal probability in this case. So there's no, here, the quantum outcome of my measurement of the first spin taken in and of itself is not guaranteed. All that's guaranteed is once I make that measurement, the other spin is completely determined. So this can lead to, this classically led, this kind of state was introduced by Einstein, Podolsky, and Rosen and has led to a lot of headaches because one can prepare such a pair of spins and then separate them. And then a measurement of one, by measuring one, you instantaneously know what's going on over here, and it sounds like something very non-local has occurred. Of course, there's no way to pass any information because you don't know what you're going to measure too. And B, you presumably had to first prepare these spins. When you first prepared these spins, you prepared them when they were close to each other in a perfectly causal way, and then separated them. So in that sense, I don't think that kind of non-local, the apparently non-local result is particularly a surprise or violates any known laws, but it does tend to make people a little bit uncomfortable. But nonetheless, entanglement is a real thing, and you can prepare such entangled states and measure them. And so I'm not going to worry about any of these philosophical issues. Just as I read, I tend to think that a lot of the weirdness of quantum mechanics comes because it operates at microscopic scales, at the atomic scale, and of course we mere humans are very large objects made out of 10 to the 23rd atoms, evolved to deal with other dangers of similar size, and so it's not surprising that our intuition for quantum mechanics is a little faulty. Okay, so my goal is then to walk you through some of the basic concepts in and applications of quantum entanglement. Before I go on, I'll say there's a number of good books and online resources for this subject. And let me just, I didn't get around to giving websites, but I'll mention just two. One is a book by Chuang and Nielsen, which I believe is called Quantum Information. And then there are lecture notes on quantum information by John Preskill. And I don't have the website, but I checked last night. If you just Google lecture notes, quantum information, John Preskill, you'll get his webpage. And those notes are excellent as well. I've learned a bit from them. Okay, so by way of outline, let's put this over here. First, I'll talk about some basic concepts. I'll say a few words about these kinds of bipartite systems and give a first operational definition of entanglement once I've set up a little bit of math. I'll introduce density matrices. Say things about that, and then I'll jump into applications. Which is advanced coding, quantum teleportation, which isn't quite as exciting as it sounds. It's the ability to send a qubit across it. And finally, I will a bit about decoherence. And if by some miracle the time hasn't run out, I'll try to say at least a few general words about the emergence of thermal behavior in closed quantum systems, for which entanglement is a central concept. So by bipartite systems, I mean exactly the situation which I stupidly just erased. So I'm going to let the Hilbert space, again, be some sort of tensor product. And in general, this could have dimension m and an orthonormal basis of n independent unit norm vectors. And this will have dimension m with an orthonormal basis mu, where mu goes from 1 to m. And I will assume without any loss of generality that n is bigger than m, because it doesn't really matter which order I take the tensor product in. So this is just to fix some notation. And as before, I can write down a general state psi. In general, I can write psi in the following way as a sum over I and mu times some coefficients where, of course, Ci mu is complex and the sum over I and mu, Ci mu squared is equal to 1, guaranteeing that this state has unit norm. Now, what I want to give you is some notion of, some precise notion of an entanglement. This is a general decomposition of the state, and what we don't know in advance, if it always has to be, is, you might ask the question, does psi have to be written like this? As a sum, or does there exist a basis such that, say, psi is equal to 1a, 1b, so that psi factorizes cleanly? In this case, well, certainly the measurements are correlated. It's sort of if I measure along this basis, it's correlated. In general, what you measure here doesn't care about what you measure here. It's, there's no, so I want to try and distinguish these in some clean way, and a priori I could start with a situation like this and do some unitary transformation to bring me to this. So let me try to get a slightly cleaner characterization. I'm just going to use, I can think of Ci mu is an n by m complex matrix. So I can do a singular value decomposition. By which I mean that I can write C as an n by m matrix as U I mu I alpha sigma alpha beta 0 b beta mu. Here I'm summing over repeated indices. And this is an n. This is an n by n unitary matrix. This is an m by m unitary. This is a m by m diagonal matrix. And this is a n minus m by m matrix of zeros. So I can always do this, and furthermore, it turns out that sigma I can write as its diagonal, and d sub alpha is real, and it's greater, and they're all greater than or equal to 0. So I can always do this. And then in this case, I can write a new basis alpha in A, which is going to be the sum on I, U, I, alpha, I, for alpha equals 1 to m, and then I can take and then find a basis for the orthogonal complement. So by which I mean this basis here, alpha only runs from 1 to m, which is generally less than n. So this will span a subspace spans an m-dimensional subspace H tilde A. So here, this will perform a basis for that subspace. If I wanted to find a full basis, if I wanted to find an orthonormal basis that included these, I would just figure out the orthogonal complement and then find the additional basis vectors for that orthogonal complement. But this we'll call H tilde A. And similar, so I can write down this new basis vector, and let me just show that it's orthogonal or orthonormal. So if I write alpha A, beta B, well, this is going to be U dagger alpha I, U, J, beta, J, where again I've summed over all repeated indices, or if you like, I, J. Now, the inner product of, because I started with an orthonormal basis here, Ij, this becomes sum on I, U dagger alpha I, U, J, beta. But I told you these are unitary matrices, and for a unitary matrix, the Hermitian conjugate is the inverse. So this is just delta alpha beta. And it's pretty easy to show that similarly, I can write down alpha B is equal to V alpha, how did I write this out? V beta alpha mu times mu is also, this is an orthonormal basis. For Hilbert space B, and it will cover everything because this is, I have V is M by M, and I have M of these vectors, and I'm good to go. Using this fact, I have psi equals sum on I mu. And now I've written this as U I alpha sigma alpha beta V beta mu times I mu. But U times I gives this, you find pretty quickly, is just sigma alpha beta alpha A beta B by the formula I've just given you. And this is just sum on, because sigma is diagonal, E alpha, alpha A, beta B. So I can always find a basis where I bring this state into the diagonal form. And I can now define the an invariant number, which is the Schmidt number, which is the number of non-zero diagonal elements. Of sigma. Okay. Can always do this, and then if, so let me call S, if S is equal to 1, the state is unentangled. Because psi is just this product. Otherwise, it's entangled. So I can, in some reasonably invariant way, bring my state into a form where I can just diagnose straight off, where I can give a straight, clean definition of whether this state is somehow entangled or not, or whether there's some way to bring the state into a form, into a product form, where the measurements are completely uncorrelated. It won't be, so if I started with the basis of spins, it would not in general, well, if I started with the basis of spin along the z direction, it would, if this was a two-state system, it may not be spin along the z direction. In that case, it would be spin along some other direction.
That you can actually measure at this point.
Well, no, I mean, I can always, it's a basis, I can always design a, well, practically that may be true. So just in principle, any Hermitian operator is a potential observable. The Hermitian operators in this case would just be the projectors onto the different basis elements. Those are Hermitian operators, and so then the question is, does my experimental apparatus allow me to do that? Now, in the case of spin 1/2, I think you'll always find that the result is spin along some axis. And so as long as you're able to orient your device appropriately, you're good to go. But yeah, it could well be that practically speaking, there's some observable that, and that once I get to sufficiently complicated quantum systems, they're often Hermitian operators that you would never observe. They're horribly non-local and or something like that. And you're describing some field theory, and there are many horribly non-local Hermitian operators that you could never build an apparatus to measure. I mean, that's certainly possible. And it's quite possible that in that case there could be some Schmidt decomposition which relates it to some basis elements that you could never really isolate in any reasonable way. I haven't really thought about it. Yeah. Okay, just a quick comment before I go on. Again, I've said that d alpha is greater than or equal to 0. It also has to be true, and it's real. It also has to be true that the sum of the squares is 1 for this to be normalized. So this already guarantees that these are between 0 and 1. And furthermore, the standard rules of quantum mechanics tell you that the square of d alpha is the probability of finding either A or B in state alpha. Okay, so the second, with eventually some help from this mathematical result, the second thing I want to introduce is the notion of a density matrix. This is abstractly I can talk about the state in quantum mechanics as a vector in a Hilbert space, and then there's some rule for determining what happens when I try to make a measurement associated with some Hermitian operator. The probabilities that the measurements work out a certain way. Now, all of that's well and good if I at least know or can determine with complete accuracy what my initial state is. But often in the real world, you don't, in fact, probably most of the time, you don't have that kind of precise information. The classic example is when I get some unpolarized beam of, say, neutrons, as in the Stern-Gerlach experiment, and typically the neutrons will be, say, spin up or spin down with respect to some direction with 50% probability. So each neutron that I measure by passing it through the Stern-Gerlach device, I don't necessarily know what its initial state is, and density matrices, among other things, are a way to try and deal with that within the framework of quantum mechanics. So, but more generally, this uncertainty can occur if there's some uncertainty. So let's say I'm trying to measure some state of some system H. And I'm I'm going to approach the description. I'll get the same sort of mathematical construct, and I'm going to approach the. I'm going to approach the uncertainty in two separate ways. There's by saying there's two things that can happen. One is that psi is drawn from some classical probability distribution with probability p sub alpha. So alpha can run from 1 to, say, little n. This isn't the same alpha as before. I'm just running out of indices. And furthermore, these do not have to be orthonormal. It could be that I draw, say, state which is spin up with 50% probability, and a state which is spin aligned along the x direction with 50% probability. Somehow that's the uncertainty. Those two states are not orthogonal to each other, but it's a perfectly reasonable possibility. The second possibility, so I'll go back and talk about density matrices in this context. The second possibility is the observed system is a subsystem of a larger quantum system so HA is a subset of H, and furthermore, the state is entangled between HA and its orthogonal complement. So because it's entangled, the state, if I try to measure the state in HA, there isn't any definite answer. Rather, measurement, it will correlate with what's going on in HA dagger, but I could imagine, for example, if there's some Schmidt decomposition, which particular state I get will occur with some probability, like so. In some sense, these aren't completely different. I mean, the universe is, as far as I'm concerned, the universe is quantum. And I could, in principle, describe everything using quantum mechanics, including classical observers, if I understand the classical limit well. And so I could, in principle, phrase this situation in this language. But that's a little bit complicated. There is certainly a qualitative difference between quantum and classical, so I'll try to keep these discussions separate. I should say, usually the separation between quantum and classical, at least in the past, had been something you could afford not to worry about. You could just use the Born rule and forget about it, and for most of us, that's good. But if you study quantum cosmology, where everything starts as a quantum fluctuation, all the structure, the cosmic structure that we see today, according to inflation, is the result of quantum fluctuations in the early universe. You're then stuck with this uncomfortable question, well, okay, how did the wave function collapse? Who measured this wave function? And it then sort of points out that you need to find some way to, at least in principle, to describe everything in the context of quantum mechanics and see how classical behavior emerges. Explain why, even though you get some quantum wave function for the structure of the early universe, you don't see quantum superpositions of different galaxy distributions on the sky. That's an interesting question. It's never been, I think, actually totally answered, at least to my satisfaction and to many's. I'm not sure what practical use it has, but it's certainly something one should try to understand. Okay, so let me start with case. Let me just label these here. Case 1 and case 2. So case one, what I want to do is compute, the best I can do, of course, since I don't know what the state is to, I know it's drawn from some probability distribution. To try and figure out what's going on, to figure out the probabilities, I just make large numbers of measurements and try to compute the results of, say, the measurement of some Hermitian operator after, or different Hermitian operators after large numbers of measurements. And the results of that measurement is of Hermitian operator. The result of that measurement can be summarized in an expectation value, which is sort of the average over all of the measurements. And so in finding the average, the first thing I do is sum over all the different possible initial states. Given an initial state, the average of a series of large, the average of a large number of measurements of this operator in that initial state is this expectation value, this matrix element of the operator. So now if I let K be an orthonormal basis of HA, I can represent the identity like so. And it's a standard trick in deriving various quantum identities to take the identity operator and stick it in various places in your matrix element to try and get interesting new results. It's really stupid, but it works. So I can write, I'll call this the expectation value of A hat. So A hat I can write now as sum on K and alpha of P alpha, psi alpha, K, A hat, psi alpha. And all I'm going to do now, these are just complex numbers, matrix elements. And so all I'm going to do is use the fact that complex multiplication commutes. So I can write this just as well. Psi alpha, K. And now I can define an operator, rho hat, as the sum on P alpha, psi alpha, psi alpha. And if I've given an operator, if I'm given an and so A hat is the sum on K, A hat rho K, which is just the trace. And this is just a fact about traces that it doesn't matter, that I can cyclically permute the matrices inside a trace. So I'm left with this operator, and the point is that the results, the trace is a basis-independent thing. I can perform this trace on any basis. All of the results of the experiment are, or any, the expectation value of any operator is going to be written down in this form. So I know the results of all experiments if I know this object, and rho hat is what I call the density matrix. So before going on, let me just say a few words about the properties of this density matrix. Well, first, it should be clear that if P was a probability, so therefore it's a real number between 0 and 1. I should have said that here. So it's really P alpha is between 0 and 1, and sum on alpha, P alpha, is just 1. So furthermore, it's got to be true that trace rho hat is equal to 1. This fact encodes, the second property encodes the statement that this corresponds to a set of states drawn from a classical probability distribution. A few words about, I want to say a couple words about dynamics. The dynamics really depend on the assumption of how things start. A typical textbook case occurs where I draw this state from some classical probability distribution, but once I've done so, this state, all states in the Hilbert space, evolve according to some Hamiltonian which I know perfectly well and which acts within the Hilbert space. So if the dynamics in H is described by a Hamiltonian H, so that I H bar dt, the evolution of any state is described by the time-dependent Schrödinger equation. Then from this, I get a nice simple evolution law for the density matrix. In this case, this means that I H bar dt rho is equal to sum on alpha P alpha I H bar dt psi alpha. So I imagine here that I'm drawing plus sum on alpha P alpha psi alpha of t I H bar dt psi alpha of t. In writing this, I'm making the assumption that I draw from my state from a probability distribution at some fixed time t, say t equals 0, and after that time, this state evolves according to the time-dependent Schrödinger equation. And in this case, that h hat psi alpha of t, psi alpha of t, and by taking the complex conjugate of this time-dependent Schrödinger equation, I get P alpha psi alpha of t, psi alpha of t, h hat, where this minus sign comes from the complex conjugate of the time-dependent Schrödinger equation, but it's pretty easy to see that this is just h hat rho hat. So I get an equation that looks an awful lot like the Heisenberg equation of motion for an operator, except there's a difference in sign. Because this is really describing the evolution of states in the Schrödinger picture. So this was indeed an assumption. In general, of course, the very fact that I'm sitting there drawing this thing from some probability distribution, meaning the state was initially coupled to some other stuff about which I'm uncertain, I might not be able to, even after time t equals 0, isolate this system completely. In this case, I'll come back to the case where this system is part of a bigger subsystem, and the two systems interact, quantum system, the two systems interact quantum mechanically. And I'll talk about that more general case in that framework. I mean, the simple coupling, of course, could just be, it's described by Hamiltonian evolution, but there's some external control parameter. You could try to give a classical control parameter, which just appears as some time-dependent coupling in the Hamiltonian. That would be a simple sort of classical interaction, but I'll talk about this more general case next. So let me talk about B, the case of open quantum systems. So here, I'm imagining that the full Hilbert space is a tensor product of the system times something called the environment. And the system is the thing that I observe. And this is the environment is all of the degrees of freedom that I'm not observing directly. And this could, of course, be, if I have some spin, it could couple weakly to other spins I haven't bothered to observe. Or if I'm trying to describe the quantum mechanics of some particle in an imperfect vacuum, I might not be observing the gas molecules in that imperfect vacuum. And so the full Hilbert space would be the tensor product of the Hilbert space of the particle and the Hilbert space of all the other gas molecules. And so this is certainly the most general situation. The best I can do is to try and decouple these as best as possible. But in general, you will get couplings like this. And this whole subject of how to treat this situation, how to find the dynamics of, how to understand the dynamics of the system when it's coupled like so, when I don't know anything about the environment, is the subject of open quantum systems. And it's a major subject of research now, in which, as far as I can tell, there still remain lots of basic confusions one could profitably disentangle. No pun intended. So once again, in this situation, I have the full state as before. So now I'm replacing what used to be A and B with system and environment. And now let's say A hat, let's say I have an observable, which I'll call A hat S cross 1 acting on the environment, which I'll call, just by shorthand, A hat. So this is an observable which acts non-trivially on the system and acts trivially on the environment. And that's the kind of thing. I mean, imagine that I'm going to measure the position of the dust particle or the spin of some neutron, and I'm not going to make any measurement of the other gas molecule sitting in my imperfect vacuum. And so now if I want to know the expectation value, there's the state of the system. The system is not in a definite state in general. In general, this will be an entangled state. And in this, if I now try to take the expectation value of the measurement of an operator, if I prepare this state a whole bunch of times, then I'll find that this is just the sum over I mu and J nu of nu J C star J nu A hat C I mu I mu I nu. Can people read these indices in the back? Okay. So A here will act on non-trivially on I and J, but not on mu and nu. And this is an orthogonal basis. So using the fact that mu nu is delta mu nu, I'll find that this is C star mu J mu C I mu J A hat I. And now I can perform the same trick as before. I can insert if I again write 1 the identity operator acting on the system in this way. This, by the way, is sometimes called a resolution of the identity. And there are an infinite number of equivalent ways of doing this because there are an infinite number of basis vectors of orthonormal bases in a given Hilbert space, a continuum of them. I can do this here, and so I'll find that psi a hat psi is going to be the sum over mu ijk. I'm going to finally call rho ij is the sum on mu c star j mu c I mu. And this, by the way, as a matrix, is a Hermitian matrix, as you can convince yourself. So I'll get mu rho ij, j, I do this, a hat, k, k, I, and now I can just write this as sum on mu ijk, k, I, rho ij, a, k. And this is again equal to trace rho hat A is equal to trace A rho hat, where rho hat is the sum on I and j of rho ij. So once again, in this case, I found an almost identical argument as before, in which the expectation value of an observable of the system is encoded in the trace of that observable times some matrix, rho hat, which is Hermitian, and furthermore, you can show that certainly rho dagger is equal to rho, and trace rho hat is equal to 1, as before. And this satisfies all of the properties of a density matrix, and is sometimes called the reduced density matrix. It's the density matrix I get by taking a full quantum system and reducing it by tracing out the results of the environment in this way. I can equally well write rho hat is the trace over the environment. And I'll leave that formula as a simple exercise. Any questions? Sorry, what? So, well, the environment may or may not be entangled with the system, so let me step ahead and talk a little bit about that case. So let me go back to the state that I started with. Remember, I can use the Schmidt decomposition to write psi as the sum on some alpha of d alpha, alpha, alpha. And so if the state is unentangled, I can write psi as, by choice of labeling basis, this. And now a hat is just 1, a hat 1. It's just what I would expect for an expectation value if the system was in a definite quantum state. And so I get a density matrix. What I'll find is that rho hat in this case, which is trace H environment, is going to be the sum on alpha environment, alpha rho hat alpha. What I'll get is indeed just 1 system, 1 system. Whereas if the state isn't so if the state isn't an if psi is entangled, then using the Schmidt decomposition, I'll find more generally that rho alpha takes this form, d alpha squared times alpha alpha. And so, which I'll write p alpha is equal to d alpha squared. And so now I've got a situation where if the initial state is in state alpha according to the Schmidt decomposition with probability p sub alpha. And if the state is entangled, there's more than one possible initial state. And so if, say if p alpha is equal to 1 for some alpha and 0 for all others, this is called a pure state. And when you get a reduced density matrix, you will get a pure state whenever I start with an unentangled state in the full Hilbert space. And if p alpha is not equal to 0 for more than one alpha, I get a mixed state. And in this framework, a mixed state emerges whenever my initial state is entangled. So let me just say a word about dynamics, and then go on to a couple of simple applications. In general, the dynamics of rho is not in general Hermitian. In general, my Hamiltonian acting on the full Hilbert space might be the Hamiltonian of the system acting on the system only. There will be a term acting only on the environment, but then there will be some terms where I can sum over some A, O, A system cross O, A. Some additional interaction terms which couple the system and the environment. And then certainly it will be true in the full Hilbert space if I write psi. Remember, the density matrix at any given time is going to be the trace over the environment of this state, which is going to be the trace h environment of e to the minus I ht psi psi e to the I ht. And rho hat is going to be the trace over he of the full Hamiltonian commuted with psi of t, psi of t. But there is, in general, absolutely no reason for this to be any kind of commutation relation like this. In general, there will be no way to do this. And without going into any derivations, this is a whole other subject. If I start with an unentangled state at time t equals 0, I may start with an unentangled state, but when I evolve it forward in time, there are interactions, and the state won't remain unentangled. The state will entangle itself, will become entangled due to the interactions. And you can show that in this case, the evolution equation has the following form. I'll call someone M, Hm of t, Lm of t, rho hat, Lm dagger of t, minus 1/2 times an anti-commutator. This is not the most general evolution equation. It's true when this, when at time t equals 0, I have this initial state. I have this term which is Hamiltonian, and this term which is not. And this this occurs because over time the Hamiltonian will induce transitions in the environment which are somehow related to what's going on in the system. Just as a note, if H here, this is a set of numbers, of real numbers. LM are just some set of operators. If H and L are time independent, and HM are greater than or equal to 0 for all M, then this is what's known as the Kossakowski-Lindblad equation. And by a certain definition of a quantum, what Kossakowski and Lindblad showed, if you adopt a certain abstract definition of a quantum Markov process, the evolution equation of the density matrix is of this form. In general, these evolution equations are called master equations. This is a particular kind of master equation known as, sorry, this plus sign, known as the time local master equation, and then the Lindblad equation corresponds to this case. And that, again, is a whole other subject. In general, dynamics are not Markovian. In general, the initial state isn't even that, and the general form of the master equation is not known.
Presumably those L's you can, in some sense, come from the last term in the Hamiltonian?
Yeah, I can, and for example, in perturbation theory, I can write them down as matrix, to say second order in perturbation theory, they're just matrix elements of the interaction term. Okay. So I want to finish up with a couple very simple applications of quantum entanglement. I'm going back to the state of two-spin, using entangled states of two-spin, one-half particles. And these are things that were discussed very briefly in a Purvis talk, and I just want to go over them in a little bit more detail. Now, in general, I'm going to consider systems of qubits. A qubit is a system with Hilbert space H qubit equals C2, so it's mathematically identical to the Hilbert space of a spin one-half particle. And again, there's going to be a basis. I can choose any orthonormal basis, 0 and 1, which might be, for example, it does not have to be the spin up and spin down states of a spin one-half particle as measured in the z direction. This is distinguished from a classical bit, which is a system with two states, 0 and 1, because in a qubit, the state can be written as R0 plus e to the I alpha, 1 minus R, half, 1, where there is a continuous set of possible states of the qubit, as opposed to the classical bit where there's only two states. So now the game, what I'm going to be telling you is two examples in communication. I'm going to consider two different possible types of communication. I could communicate via classical channel to observers, send a classical bit, which I'll call a C bit, which is a 0 or 1. Or I could talk about a quantum channel I send a qubit hi. And what I'll argue in these two examples is that in general, the quantum channels of a single qubit encode more information than a classical channel. And the two examples I'll give you, the quantum channel, I can send 2 classical bits using a qubit, or I can send complete information about a qubit using 2 classical bits, assuming I have some initial entanglement resource that I can draw on. So let me just give you those 2 examples, and then I'll finish up. The first example is quantum dense coding. Which uses a quantum channel. And so what I imagine is I have, so I'm going to start by noting the following thing. If I take the space of 2 qubits, has a basis phi plus minus is equal to 1 over root 2, 0, 0, plus or minus 1, 1, and psi plus or minus 0, 1, 1, 0. These are 4 total states. You can show very quickly that they're orthonormal. The space of 2 qubits is the tensor product of 2 two-dimensional Hilbert spaces, so it's a 4-dimensional Hilbert space, so the counting works out all nice. And notice that these are all maximally entangled. For example, for any of these states, the reduced density matrix, so if I call these 2 2 qubits A and B, the reduced density matrix for the first qubit A is just half of the identity. So the Schmidt number is maximal in that case. So now what I'm going to imagine is that I have 2 experimentalists, and classically in the quantum information literature, the experimentalists are called Alice and Bob, after A and B. I don't know the total history. In some sense, this is clearly an attempt to make these discussions at least somewhat gender neutral. Unfortunately, they introduced a rather strong bias towards nice white Anglo-Saxon Protestant names. When I teach, I try to break that a little bit. You can, in your head, substitute any other names that you like. Okay, so now what I'm going to imagine is that my 2 experimentalists, let's say my 2 experimentalists, and I'll just stick with Alice and Bob, prepare a bunch of pairs in the state phi plus or minus. They're only, say phi plus, they're only going to use, and then each Alice takes qubit A of each pair, and Bob takes qubit B of each pair. And that's going to be the resource they're going to start with in both of these experiments. Now, what I claim is that Alice can send one of 4 possible messages by taking her qubit, manipulating her qubit, and then sending it back to Bob and having Bob make a measurement. And the results of Bob's measurement will be determined by the operation that Alice made. At this point, I've only sent a single qubit. I've done a manipulation before, but I've only sent a single qubit, and I claim I can get one of 4 possible results, the same as if I've sent 2 classical bits. And that's the dense coding, that a qubit contains more information than a classical bit. So let's say if Alice, so the 4 possible interactions are first that Alex acts with the identity. If I act with the identity operator on her qubit, it's clear that that will do nothing. It will map phi plus to itself. She could also act with sigma 1, which in the basis if I write out these vectors in the Hilbert space in vector notation in this way, the sigma 1 operator will have this form. So in particular, sigma 1 acting on 0 is equal to 1, and acting on 1 is equal to 0. And if I go back and look at phi plus, I'm going to flip the first bit. So I'll get 1, 0 plus 0, 1. So sigma 1 acting on 1 over root 2, 0, 0 plus 1, 1 is equal to 1 over root 2, 1, 0 plus 0, 1, which is equal to psi plus, because this only acts on the first bit and flips it. So if she acts with sigma 1, if she acts with sigma 2, which is 0 I minus I 0, then sigma 2 phi plus is going to be equal to I times psi plus. And this factor of I is just an irrelevant phase sitting out in front of the final state. And finally, if I write down sigma 3, which is equal to I times phi minus 1, 0, 0, sigma 3 acting on phi plus gives me phi minus. So she can choose one of 4 different operations on her qubit, which will take the entangled state, phi plus, and map it to one of these 4 orthonormal entangled states here. And then she sends her qubit to Bob. And then Bob now has a pair of qubits in one of these 4 states. These are orthonormal states, so Bob can, with a single measurement, so B can measure, keeping all these up. He can design an operator O, which might be, say, minus 2 phi plus minus phi minus plus psi minus plus 2 psi plus. And by measuring which of these numbers I get, by taking this operator, the outcome of the operator will tell me which of these 4 basis states Bob has. And so he now has complete information about which of the 4 things Alice did, and she's able to send a message. So now I just want to go. Are there any questions before I go on? The second thing I will try to do is see how many classical bits I need to send a single quantum bit, and the answer will be, by construction, be 2. So again, Alice and Bob prepare a bunch of bits in the state psi plus, take them away, and so they have these shared entangled qubits as a resource to communicate somehow. And let's say that Alice has a qubit, another qubit, chi, and she wants to communicate to Bob what the state of that qubit is. And now you might think I mean Chi, the argument is going to be that Alice can do this with 2 classical bits. Now that sounds a little bit, a priori that sounds hard because Chi could be in one of an infinite number, continuous infinity of states, and I'm communicating that with 2 classical bits. But very crucially, I'm going to use the existence of these entangled pairs as a resource to do this. So the initial state of the full, I'm going to start with the initial state of the full system of the qubit that Alice wants to send and one entangled pair, which is shared between Alice and Bob. So I'll call this Chi message, and then 1 over root 2, 0A, 0B, plus 1A, 1B. Now I can write Chi as A0 plus B1. This is an orthonormal basis. Sorry, it's a 0. And I can now expand out psi is 1 over root 2 times A 0, 0, 0, which is MAB plus A 0, 1, 1 plus B 0, 1, 0, 0 plus B 1, 1, 1, like so. Now, what I'm going to do is take this state and write it down as the tensor product of the pair of the message bit and Alice's bit times the state of Bob's bit. And so similarly, this I can also perfectly well write down these as basis vectors for the tensor product of the message bit and Alice's bit. So in particular, using, for example, that 0 message, 0 Alice is going to be equal to 1 over root 2, 1/2 times phi plus phi minus, where these are basis vectors in entangled basis vectors of the Hilbert space of the message bit and Alice's bit. And so using that, I can write psi 3 as 1/2 A times phi plus MA plus phi minus MA times 0. That's this first state in the sum, and I can keep doing this plus 1/2 A psi plus MA plus psi minus MA times 1. And this is all Bob's bit plus 1/2 A psi minus minus psi plus minus psi minus, sorry, 1/2 B times 0 plus 1/2 B phi plus minus phi minus 1B. Okay. And finally, just regrouping, I find that psi is going to be equal to 1/2 phi plus ma times a0 plus b1 plus times a0 minus b1 times a1 plus b0. Bob plus 1/2 psi minus so now I can write, I've written the initial state in terms of the tensor product of the sum in this decomposition where here I have the different 4 different orthonormal possibilities for the state of the 2 qubits that Alice has in her possession and some complicated state. And which state Bob measures depends on which of these states Alice measures. So now Alice measures with O this operator here, which tells her which of these states she's got. And then she sends result to Bob with 2 C bits. Because there's 4 possibilities, so she just needs 2 classical bits to tell Bob which of the 4 possibilities she actually realized. And given a possibility, Bob's state will be one of these. And the final thing Bob does is just say they've agreed on this protocol in advance. Knowing some quantum mechanics, they've agreed on the following protocol in advance. If Alice measures phi plus, Bob does nothing. And his qubit has a state, the state chi, which is the same, identical to the state of Alice's message qubit. Now, if Alice measures phi minus, she sends that result to Bob, and then Bob applies sigma 3, and it's sigma 3 acting on A0 minus B1 is equal to A0 plus B1, which lo and behold is equal to chi. If A measures psi plus, Bob applies sigma 1, which is 0, 1, 1, 0. And indeed, sigma 1 acting on A1 plus B0 is equal to chi, because the job of sigma 1 just flips each bit, like so. And finally, if A measures psi minus, B applies sigma 2, which is 0, I minus I0, and sigma 2 acting on A1 minus B0 is equal to I times chi. So they've agreed on this protocol in advance. So all Alice has to do is say, OK, I made this measurement. Bob says, OK, you've made that measurement. I apply the corresponding operation towards the protocol. Whatever happens at the end, the bit that Bob ends up with is in an identical state to the bit that Alice was trying to send. And so using 2 classical bits plus the shared entanglement resource, I can send a quantum bit which is described, of which there is a continuous infinity of possibilities. The entanglement resource here is absolutely essential to this. Okay. The last thing I wanted to talk about, and I've only got a few minutes, so I won't say much, is about decoherence. And this is a general phenomenon that occurs indeed in the kinds of open quantum system cases I've talked about, where I have a system I'm trying to measure, and I might try to prepare that system in some definite superposition. And the sort of quantumness of the state is tied up in the fact that I can create different superpositions. I mean, one of the classic experiments one does to sort of see how weird quantum mechanics is the double slit experiment, where I fire a massive particle to a screen with two slits, and what I get is an interference pattern generated by the wave function of that particle, and that wave function of that particle has support on the particle having gone through either slit. So the fact that I can have a quantum superpositions like, psi of some particle is equal to x1 plus x2, appropriately normalized, and I can have interference when I make measurements. The measurements can have interference effects, which is, say, I could have some x1 psi a psi is equal to x1 a x2 1 plus x1 a x2. I can have these interference effects coming from off-diagonal terms, and that's the hallmark of a quantum measurement. And the issue with and it's because these occur with definite phases. The issue with decoherence is that once I couple my system to other stuff, I can start with a state like psi and then chi times the environment. And when I evolve this forward in time, I can end up with a situation like this. So in particular, I imagine I have some heavy particle, a dust particle, that's sitting in a bath of photons. These photons might just be the black body photons at room temperature, or even the cosmic background photons. The photons won't disturb the position of the particle very much over a short time, but they will scatter off of the particle, and the position of the particle will determine the details of how they scatter. And so the state of the photon will depend, over time, will depend on the state, the position of the particle, and I can evolve to a situation like this. And now I have a completely entangled state. In particular, if these two end up being orthogonal or close to, I have a completely entangled state where I've lost the relative phase information between here and here. In particular, in this case, what you can show is that if I look at, say, a hat acting on the system, I'll get, say, x1 a hat x1 times, say, psi1 plus x1 a hat x2 psi1 psi2 and so forth. And because I'm running out of time, I'll just measure that there's a very, I'll commend to you a very nice paper in the 80s by Joos Zen, B 59 223. This is from back in the 80s. And what they did is considered the system as being some, say, heavy dust particle, a micron in size, and in some position eigenstate like this. And they considered this in the bath of either photons or air molecules, and they had some model for how the photons interacted with the dust particle, or the air molecules interacted with the dust particle. And in general, what they found is that if I looked at, say, the density matrix, tracing out over the environment, say, of photons of the full state, which evolves like so, what you find is that this is x x prime times e to the minus gamma x minus x prime, and I'm just done. And so let me just draw a few numbers here. In the calculation they did, so here this has units. So imagine I have a dust particle a micron in size, and if the environment are just the CMB photons, then lambda is 10 to the 6th centimeters squared second. So in particular, if these dust particles are a centimeter across, it will take 10 to the minus 6 seconds for these off-diagonal terms to die off completely, and for me to end up in a completely mixed state of a photon here and a photon here. If it's room temperature photons, then lambda is of order 10 to the 19th. And if I instead use air molecules, I think lambda, they argued, is order 10 to the 23rd. So this calculation involves a lot of assumptions, but they're not unphysical. And the point is that this decoherence, this destruction of this phase coherence happens at an extremely short time scale. Among other things, it's something you always have to worry about when you're actually trying to prepare the state of a quantum computer to do some computation. And a lot of effort has to go into sort of protecting the quantum nature of your qubits and protecting the fact that they're in some definite state. But it also tells you why I never see in nature this quantum superposition of a dust particle here and a dust particle here, or the quantum superposition of two different galaxy distributions on the sky. We never see a cat that's both alive and dead simultaneously, because inevitably all of those will interact with the environment, and what you'll see is one or the other with some specific probability. And so thanks again, and I apologize for the cock-up with Fernando, but hopefully this was at least somewhat useful.